Hey everyone, and welcome. Today, we're jumping into a super powerful tool from multivariable calculus, the cross product. So picture this. You've got two vectors hanging out in space, and you absolutely need to find a third one that's perfectly perpendicular to both of them. How in the world do you do that? Well, you're in luck, because that's exactly what the cross product was born to do.
So, what is this thing really, and what makes it so different? If you've been working with vectors, you've probably run into the dot product. But trust me, the cross product plays a whole different ballgame. It gives you a totally different kind of answer, and it's one that's incredibly useful in everything from geometry to physics. And right here, this is the fundamental difference. When you calculate a dot product, you're basically squishing two vectors down into one single number, a scalar. But the cross product, it's a creative force. You feed it two vectors, and it actually builds an entirely new vector, complete with its own direction and its own magnitude.
And the single most important feature of that new vector is that it's orthogonal to the two you started with. That's just a fancy way of saying it points at a perfect 90-degree angle to both of them. Imagine your first two vectors lying flat on a table. Their cross product would be pointing straight up at the ceiling.
Okay, so that's the what. But how do we actually find this new vector? Well, for that, we're going to borrow a really handy tool from linear algebra, the determinant.
Now, don't let this matrix scare you. This 3x3 determinant is really just a fantastic organizational tool. It's a way to calculate the cross product without having to memorize some long, messy formula. All you do is set it up with the standard unit vectors, our friends I, J, and K in the top row, and then you pop the components of your two vectors, A and B, right underneath.
And to solve it, we use something called cofactor expansion. For the I component, you just imagine covering up its row and column, and then you find the determinant of the little 2x2 square that's left. Same thing for K. But, and you have to listen to this, the J component is the one that trips everyone up. See that negative sign in front? You've got to have it. The pattern is always positive I minus J positive K. Please burn that into your memory. It'll save you so many points.
All right, enough theory. The best way to get comfortable with this is to just do it. So let's put this formula to work. We're going to walk through 3 examples, and each one's going to add a little something new to our understanding. For our first one, we'll keep it pretty straightforward. Let's say we have vector A, which is 1, 3, 4, and vector B, which is 2, 7, negative 5. The goal is simple. Find their cross product.
So we set up our determinant, just like we learned. For the I component, we get 3 times negative 5, which is negative 15, minus 4 times 7, which is 28. That gives us negative 43I. Now for the J part, and remember that minus sign. It's minus J times 1 times negative 5 minus 4 times 2. That whole thing becomes minus J times negative 13, so it flips to a positive 13J. Finally, for K, it's 1 times 7 minus 3 times 2, which is just 1K.
And boom, there it is, the vector 4313, 1. This is the one and only vector in the entire universe that is perfectly mathematically orthogonal to the two vectors we started with. Pretty cool, right?
Okay, let's level up for our second example. This time, we don't just want any old orthogonal vector, we want a unit vector. That means we want a vector that's not only orthogonal, but also has a very specific length, exactly 1.
This is always a two-step dance. First, you do exactly what we did before. Find the cross product of u and v to get your orthogonal vector, which in this case is negative 1, 0, 2. Great, but that vector's length isn't 1. So for step 2, we have to normalize it. That sounds complicated, but it just means we find its length, its magnitude, and then we divide every single component of our vector by that length.
So the magnitude or length of our vector negative 1, 0, 2 turns out to be the square root of 5. That's our magic scaling number. By dividing our whole vector by the square root of 5, we basically shrink it down just enough so its new length is perfectly 1. And that gives us our final unit vector.
And for our last example, we get to see one of the coolest geometric tricks the cross product has up its sleeve. It turns out that the magnitude of the cross product isn't just some random number, it's exactly equal to the area of the parallelogram made by the two original vectors. And this fact gives us an amazing way to find the area of a triangle.
So if you're given 3 points in space, P, Q, and R, here's the game plan. First, you make two vectors that start at the same point, like PQ and PR. Next, you find their cross product. Here, that gives us the vector 6, 3, 2. And finally, you find the magnitude of that new vector, which is the square root of 49. And then you just chop it in half. Why half? Well, because any triangle is just half of a parallelogram.
And would you look at that? The area is a nice clean 3.5. It's just a beautiful example of how this seemingly abstract vector operation can solve a very real, very geometric problem.
Okay, so we've been through a lot. After all that, what are the big ideas you should be walking away with? Let's do a quick recap of the main jobs the cross product is here to do.
So here's your mental checklist. First and foremost, if you need a normal vector to a plane, the cross product is your best friend. Second, as we just saw, its magnitude is your ticket to finding geometric areas. And finally, here's a neat little bonus property. If the cross product of two non-zero vectors is the zero vector, you know for a fact that they must be parallel.
And I'll leave you with one last thing to think about. This whole process of creating a new orthogonal vector, well, it's something that really only works this way in 3 dimensions. And that leads to a really cool question. What kind of math tools do you think people use to do similar things in 2 dimensions or 4 or even more? It's a great reminder that there's always a bigger picture out there. Thanks for watching.